SwayamPrabha. Digital India. Educated India.
Welcome to lecture 28 of the course on multivariate data mining, methods and applications. The title of this lecture is Hierarchical Clustering Techniques. Hierarchical clustering technique is an important method for clustering the observations. How we proceed in the hierarchical clustering technique? Say we start from the individual data points, then iteratively we merge the data points, all different groups of data points according to their similarity, and ultimately we go up to a point where all the data points merge in a single cluster. And so, we get a tree like diagram which is called dendrogram. We are also going to discuss different linkage methods which form the basis for merging the data points or merging the clusters at different stages. The linkage methods which we are going to discuss in this lecture include single linkage, complete linkage and average linkage. Now, we consider distance measures for quantitative variables. Now, we usually do not use the correlation coefficient as a measure of similarity. So, just we take this example where you have 3 individuals 1, 2 and 3, and you have these observations or these scores for all the 3 individuals. And suppose you consider the individual 1 and individual 3. Then you observe that the score of individual 3 is 5 times the score of individual 1. So, this 5 is equal to 5 into 1, 10 is equal to 5 into 2, 15 is equal to 5 into 3 and so on. So, there is an exact linear relationship between the scores of individual 3 and the scores of individual 1, or the correlation coefficient between 2 scores of individual 3 and individual 1 is equal to 1, R13 is equal to 1 say. Now, you can easily obtain R12 also. Of course, for first 5 observations, the scores of individual 1 and 2 are same. But here the scores are different. For individual 1 it is 6, for individual 2 it is 7. So, obviously, R12 is less than 1. Of course, it is quite close to 1, but it is less than 1. So, if we consider the correlation coefficient, then it appears that individual 1 is more similar to individual 3. But if you just look at the scores, then you observe that individual 1 and two are closer to each other. So, that is why usually we do not use the correlation coefficient as a measure of similarity. Then another distance measure is we define Dij equal to xi minus xj transpose S inverse xi minus xj, where S is the pooled variance covariance matrix of the two groups. Then this is called the Mahalanobis T square. Mahalanobis T square is a very popular measure of distance for quantitative variables. So, usually we use the Mahalanobis D square as a distance measure. Then for qualitative variables, one of the measure is genetic distance, which is a measure of the genetic divergence between species or between populations within a species. So, actually this measures the time from common ancestor or the degree of differentiation between the two populations or within a species. So, populations with many similar allies have small genetic distances. Then we define the genetic distance for two groups as, say, suppose you have gene frequencies for the two groups, then we define DAB, A and B are the two groups, as 1 minus cos theta to the power half, where cos theta is equal to summation over I PIA PIB to the power half. Here PIA is the gene frequency for the ith ally at a given locus for population A, and PIB is the gene frequency for the ith ally at a given focus for the population B. And then when several genetic loci are considered, then DAB values are added together. Now, we consider this example. So, this table actually gives the proportions of two populations of red campion flower, and you have two populations A and B. Then you have different characteristic or character state. Say the first state is corolla color, pink or white. Then for population A, the pink one ratio is 0.95, the white one is 0.05. Similarly, for population B, you have these frequencies, and then for the character state null scale as petal pink, the gene frequencies are 0.85 and 0.75. Then not as petal pink, 0.01, 0.15, and not as petals white, 0.14, 0.10. Then for the character red calyx pigment, for population A, the ratio of present is 0.8 and absent is 0.2. For population B, the corresponding figures are 0.6 and 0.4. And then we calculate the genetic distance between the two populations. So, first we consider the corolla color. So, on the basis of this particular characteristic or this particular character state, DAB is equal to 1 minus 0.95 into 0.80 to the power half, 0.95 into 0.80 minus 0.05 into 0.20 to the power half, and then we take whole to the power half. So, ultimately you get 0.17. For coronal scale color, DAB is equal to 1 minus 0.85 into 0.75 to the power half minus 0.01 into 0.15 to the power half minus 0.14 into 0.10 to the power half. You multiply these two, take power half, plus you multiply these two, take power half of the multiplication, and then we multiply these two, and then we take power half. We add all these three products, and then we take 1 minus. So, ultimately you get this value 0.21. For red calyx pigment, DAB is equal to 1 minus 0.80 into 0.60, and then we take this to the power half minus we take 0.20 into 0.40 and take this to the power half, and ultimately we take a square root of this, and finally we obtain this value. So, these are the genetic distances corresponding to different character scales, and then we calculate the total distance, which is 0.17 plus 0.21 plus 0.16, and finally we get 0.54 as the genetic distance between populations A and B when we consider all the character scales. Now, we consider hierarchical clustering techniques. Hierarchical clustering leads to dendrogram or hierarchical tree diagram, and this dendrogram or tree diagram is representation by two-dimensional diagram giving fusion or division made at each successive stage of analysis. So, at each stage we fuse two data points or two previously obtained clusters, and then ultimately we get dendrogram as two-dimensional diagram. Say K cluster solution is obtained by merging sum of the clusters from the K plus 1th cluster solution. So, suppose you are at this stage, and then we merge sum of the clusters or sum of the data points. So, at this stage you have K plus 1 clusters, and then you have merged two clusters and you come to K clusters. So, for example, this is the dendrogram of iris data. So, we draw a horizontal line on the dendrogram at a given height. Say, suppose you draw a horizontal line at this height, then you get this cluster, and then you have this cluster, this. So, ultimately you get a number of clusters, or if you draw a horizontal line here, then it leads to a cluster of points here, a cluster of points here, a cluster of points here in this group. So, ultimately you get 3 clusters, or if you draw a horizontal line here, then you have 2 clusters. So, number k of vertical lines cut by that horizontal line identifies a k cluster solution. Now, we consider the algorithm for algorithmic hierarchical clustering. Now, suppose this is your learning set. You have n observations in the learning set L, which are xi I equal to 1 to n. So, initially we start with n clusters. You have n clusters, each containing one item. Then we compute a n by n matrix of dissimilarities between the n clusters. We use some measure of dissimilarity between the data points, and since you have n data points, so you get n by n matrix. So, this is the distance matrix with ijth element dij, where dij denotes a measure of dissimilarity between xi and xj for all ij equal to 1 to n. And suppose we write d equal to d1. And then we find the smallest dissimilarity in this matrix D or D1, and say the smallest dissimilarity is D capital I capital J. Then we merge the clusters capital I and capital J to form a new cluster Ij. Then we again compute dissimilarities Dij and K between this new cluster Ij and all other clusters K, where K is not equal to Ij. So, again we get a distance matrix, and then the dissimilarities depend upon the linkage method used. So, whether you are using single linkage technique or complete linkage or average linkage or any other method. So, ultimately dissimilarities depend upon that particular linkage method. And different linkage options are single linkage. In single linkage, what we do? Dijk is the minimum of Dik and Djk. You have cluster I and another cluster K, and the distance between these two is Dik. Similarly, the distance between J and K is Djk, and ultimately you are merging I and J. So, you get this cluster. And you have to compute the distance between Ij and K. So, we take minimum of Dik and Djk. Minimum of these two is the distance Dijk. In complete linkage, Dijk is defined as the maximum of Dik and Djk. In average linkage, Dijk is defined as, we take summation over I belonging to capital I, summation k belonging to capital K, Dik divided by Nij Nk. Here Nij is the number of items in the cluster Ij and Nk is the number of items in the cluster K. So, actually this gives you the average distance between each element of Ij. You are taking I belonging to capital I, capital J. So, basically I belongs to the combined cluster capital I, capital J, and then you are taking summation over k belonging to capital K. So, you are summing all the distances and then you are dividing by the number of items in the clusters Ij and K. So, this is how we calculate the average linkage. Then form a new n minus 1 cross n minus 1 dissimilarity matrix, say D2. So, initially we have started with n clusters and your distance matrix is D1, and using one of the linkage criterion you have merged the two observations. So, now you have n minus 1 items. Again you calculate the distance matrix D2. Then we actually in D2 delete the rows and columns I and J, and then we add a new row column Ij, because basically what you are doing, you are merging these two to Ij. So, you delete these rows and columns, that is the rows and columns corresponding to I and J, and then we add a new row and column corresponding to capital Ij with the dissimilarities computed from these two steps 4 and 5. We again repeat steps 3, 4, 5 and 6 n minus 1 times, and at the ith step Di is a symmetric n minus I plus 1 cross n minus I plus 1 distance matrix, and I varies from 1 to n. So, initially you have the distance matrix D1 which is of order n cross n, then you have the distance matrix D2 which is of order n minus 1 cross n minus 1, then D3 which is of order n minus 2 cross n minus 2, and so on. At the ith step you have Di which is of order n minus I plus 1 cross n minus I plus 1. Then at I equal to n, Dn is equal to 0 and all items are merged together in a single cluster. So, we continue this process until we reach this stage. All the items are merged together into a single cluster, and then ultimately your output is a list of clusters merged at each step. The value or the height of the dissimilarity of each merge and a dendrogram to summarize the clustering procedure. So, at each step you are merging the clusters and then there is a particular value of the dissimilarity or height of the dendrogram at which the merger occurs. So, you get the information that at which distance the merging is occurring, and then ultimately you get a diagram which is called dendrogram. And this dendrogram summarizes the entire clustering procedure. Now, we consider an example of single linkage clustering or nearest neighbor technique. So, suppose you have 5 individuals 1, 2, 3, 4, 5, and this D1 is the distance matrix. So, obviously, the diagonal elements of distance matrix are 0. Then the distance between 1 and 2 is 2.0, distance between 1 and 3 is 6.0, and so on. Then we identify the smallest distance between two individuals, and we observe that the smallest distance is 2.0, which is the distance between individuals 1 and 2. Of course, while calculating or while observing this smallest distance, we do not consider the diagonal elements, which are obviously minimum 0. So, the smallest distance is between individuals 1 and 2, which is 2.0. And then we join 1 and 2 to form a 2-member cluster. So, we combine these two, and at what distance we combine 1 and 2? It is 2.0. So, you have this cluster 1, 2, and the remaining elements are 3, 4 and 5. So, from the distance matrix, now we delete the rows and columns corresponding to 1 and corresponding to 2, and then we add a new row and column corresponding to the cluster 1, 2. Obviously, we have to calculate the distance between 1, 2 and 3, 1, 2 and 4, 1, 2 and 5. So, the distance between 1, 2 and 3 is calculated as the minimum of D13 and D23. Now, notice that D13 is 6.0 and D23 is 5.0, and minimum of 2 is 5.0. So, D123 is 5.0. Similarly, you can calculate D124 also, which is the minimum of D14 and D24, and ultimately you get 9.0, and then you get D125 equal to minimum of D15 and D25, which is 8.0, and then the distance matrix for individuals 1, 2, 3, 4, 5 is, you write this distance matrix as D2, and then you have rows and columns as D1, 2, 3, 4, 5 or D1, 2, 3, 4, 5, and then we write different distances here. So, in the diagonal you have 0, then the distance between D1, 2 and 3 is 5. The distance between D1, 2 and 4 is 9, and the distance between D1, 2 and 5 is 8. And the remaining elements are the same as D1. Again, we calculate the smallest distance between two individuals, and we observe that the smallest value of the distance matrix is 3.0, which is the distance between 4 and 5. So, at distance 3.0, we are going to merge the individuals 4 and 5 in a single cluster. So, we join 4 and 5 to form a 2-member cluster. Again, we proceed as above. We calculate the distance between 1, 2 and 4, 5 and between 3 and 4, 5. The distance between 1, 2 and 4, 5 is the minimum of distance between 1, 2 and 4 and the distance between 1, 2 and 5. Similarly, the distance between 3 and 4, 5 is the minimum of distance between 3 and 4 and the distance between 3 and 5. And ultimately, we get this distance matrix D3, which has these elements. Again, in distance matrix D3, we find the smallest distance, which is 4, and this smallest distance is between 3 and 4, 5. So, in the next stage, we merge the individuals 3 and 4, 5 into a single cluster, and we do this merging at the distance 4.0, and then again we calculate the distance matrix and so on. So, finally, we get this kind of result. Say at stage 1, you have 5 clusters, each containing one individual. Then at distance 2.0, we have merged 1 and 2. So, we get 4 clusters at distance 2.0. Then at distance 3, we merge 4 and 5, and then we have 3 clusters 1, 2, 3 and 4, 5. Then at distance 4, we merge 3 and 4, 5, these 2 clusters. So, now you have 2 clusters 1, 2 and 3, 4, 5. Then finally, at distance 5, we merge these 2 clusters, and then we get just a single cluster containing all the 5 points 1, 2, 3, 4, 5. So, you got this kind of dendrogram. This is individual 1, 2, 3, 4, 5, and this merging occurs at distance 2.0. Then we merge 4 and 5 at distance 3.0. Then we merge 3 and 4, 5 at distance 4.0, and then at distance 5.0, we merge all the clusters. So, basically in single linkage clustering, what we do? We calculate the distance between 2 clusters as the distance between two nearest points. So, suppose you consider this cluster and this cluster, then the distance between two clusters is this much. Now, there are certain shortcomings of single linkage clustering. Say, in order to merge two groups, we only need one pair of points to be close. We are considering only 2 points, one point from one group and another point from the another group. The 2 points which are closest to each other in the two groups. Then clusters can be too spread out, and using the single linkage clustering, often it is difficult to discern poorly separated clusters. Then the single linkage clustering also suffers from the chaining effect, where clusters are extended by connecting individual points that are close to each other, but may not necessarily belong to the same cluster. So, we will discuss the chaining effect later on, but this single linkage clustering suffers from the chaining effect. Then sensitivity to outliers. Even a single outlier can significantly affect the clustering results by connecting distant points into the same cluster. So, this is the problem with single linkage clustering. If you have even a single outlier, it can affect the clustering results. Again, if the density of points within the cluster may vary, or there may be empty spaces between clusters, then the single linkage clustering often struggles with identifying clusters. So, if there is empty space between clusters, or density of points within cluster vary, then single linkage clustering may not be very successful. Further, single linkage clustering lead to fragmented clusters, especially in data sets with varying densities or non-convex shapes. Sometimes your data set has varying densities, then in that case single linkage clustering may lead to fragmented clusters. Or suppose the cluster is of non-convex shape, say cluster is of this type, then single linkage clustering may fail because the shape is non-convex. Then choice of distance matrix can greatly influence the clustering results. Of course, one has to be careful while choosing the distance matrix, and further, it does not provide a clear criterion for determining the optimal number of clusters. One of the problems is to find the optimal number of clusters, but single linkage does not provide an optimal criterion for obtaining the number of clusters. Another linkage method is complete linkage clustering. In complete linkage clustering, the distance between clusters is determined by the distance between elements one from each cluster that are most distant. So, in this case, say suppose you have to compute the distance between a cluster having elements I j and another point k, then d I j k is equal to maximum of d I k and d j k. So, suppose you consider this cluster and this cluster, then in complete linkage we consider these two data points which are at the maximum distance. You select one point from this cluster, one point from this cluster, and we select these points in such a manner that the distance is maximum, and then we consider this distance, the maximum distance, as the distance between two clusters. Whereas, in single linkage we consider the closest distance, say this one. Again, the shortcomings of complete linkage clustering are, using the complete linkage clustering, of course, you get the advantage over single linkage that it avoids chaining, but it suffers from another problem which is called crowding. Say its score is based on the worst case dissimilarity, means the maximum distance between pairs, and then a point can be closer to points in another clusters than the points in its own cluster. So, the clusters are compact, but not far enough apart. So, this is the problem, since you are taking the maximum distance and it may be possible that a point can be closer to points in other clusters than the points in its own. So, you get compact clusters, but the clusters are not far enough from each other. Then it also tends to produce clusters of approximately equal diameter, and in practice often we have clusters of different sizes, and in those cases it struggles. So, if the clusters are significantly different in sizes or densities, then with complete linkage clustering you face problems. Again, as we discussed earlier, it tends to produce compact clusters, but it is not suitable for detecting irregularly shaped clusters. So, if the clusters are irregularly shaped, then the complete linkage clustering method fails. This method is also sensitive to outliers like the single linkage clustering, and with the complete linkage it is also possible that we merge clusters that are connected by a few points, even if the majority of points within each cluster are far apart. Now, this is the problem with both the single linkage as well as with the complete linkage. If two clusters are just connected by a few points, but majority of points within each cluster are far apart, then these procedures may merge such kind of clusters. It also tends to suffer from the cluster fusion problem, where small well separated clusters may be merged into larger clusters, and this is due to the presence of just a few points that are relatively close to each other. So, suppose you have two clusters, one is large in size and another one is small in size. The two clusters are well separated, but just because of the presence of few points that are relatively close to each other, this procedure may tend to fuse those two clusters. Again, the procedure also suffers from subjectivity in determining the number of clusters. Of course, in practice you have to decide the number of clusters also, but the procedure does not provide you any clue for deciding the number of clusters. Now, we consider average linkage clustering. In average linkage clustering, the distance between two clusters is taken as the average distance between all pairs of items where one member of a pair belongs to each cluster. Now, suppose dik denotes the distance between I and k, and djk denotes the distance between j and k, and we have merged the items I and j into a cluster. Then, to calculate the distance between cluster ij and the individual k, what we do? We simply take the average of dik and djk, and suppose you have two clusters A and B, and cluster A has n A elements and cluster B has n B elements. Then we consider all the pairs. We take an element from here, we take an element from here, obtain the distance. So, suppose you take the element I from cluster A and j from cluster B, then we consider the distance dij, and then in cluster A you have in all n A elements, and in cluster B you have n B elements. So, we take for I equal to 1 to n A, j equal to 1 to n B, and in all you get n A into n B pairs. So, we take summation of Tij over all I and j, and we divide it by the total number of pairs, and then we get the distance between clusters A and B. So, this is how we calculate the distance between two clusters in average linkage clustering. Further, the shortcomings of average linkage clustering are: it does not have simple interpretation like single and complete linkage trees, and then it is also sensitive to outliers. Of course, it has the advantage that you are using all the pairs, whereas in single linkage and complete linkage we just use one pair of observations from each cluster to compute the distance. This method also has a tendency to produce clusters of approximately equal sizes, and then resulting in merging of distinct clusters or the fragmentation of single clusters. Then the method also has difficulty in handling non-global clusters, where the distance between points within a cluster is not uniform. Then it also has discrepancy on distance matrix. It does not satisfy the assumption of distance matrix. Then it has inability to detect complex structures such as hierarchical relationships or nested clusters within larger clusters. Again, here also you have subjectivity in determining the number of clusters. Now, we consider this example. We have 5 individuals and you have observations on 2 variables, variable 1 and variable 2. Then we consider the Euclidean distance. We calculate d12, which is equal to square root of 1 minus 1 square plus 1 minus 2 square for individual 1 and 2. Similarly, for individuals 1 and 3, it is 1 minus 6 square plus 1 minus 3 square, then we take the square root. So, it is square root of 29, which is approximately 5.39. Similarly, you can calculate d24, d25 and so on. Ultimately, we get this distance matrix, and then we are using complete linkage. So, initially we merge 1 and 2 because this is the smallest distance, and then we calculate the distance matrix D2. And for calculating the distances between 1, 2 and 3, 1, 2 and 4, 1, 2 and 5, we have used the maximum of distance between 1 and 3 and the distance between 2 and 3 and so on. Then we merge 4 and 5 at distance 2. We consider this distance matrix and we merge 4 and 5. Then we get this distance matrix. Again, we merge 3 and 4, 5 at distance 3.61 and we get this distance matrix, and then we merge 1, 2, 3, 4, 5 at distance 7.28. So, in this example, if we apply single linkage, average linkage or complete linkage, all the 3 methods lead to these dendrograms. In this lecture, we have discussed hierarchical clustering technique, which is widely used in data analysis and machine learning. In hierarchical clustering technique, actually we start from all the data points and then we calculate the distances between different data points. Initially, suppose we have n data points, then we consider n clusters. Then iteratively we merge different data points or the clusters formed in the previous steps, keeping in view the minimum distance. We have also discussed different linkage techniques like single linkage, complete linkage and average linkage technique, and their shortcomings also. So, I am going to stop here. Thank you.
Understanding oneself, understanding others, understanding society at large, understanding the nature, these are all driven by basic human curiosity. We would all love to understand why things happen, what happens, what is the final outcome, why certain things fail. These are all exercises that we perform in various domains of knowledge. Therefore, knowledge in various domains, you would realize they are actually social artifacts. They have to be rooted into historical perspective, they have to be culturally salient, and there would be socio-political reasons behind this. Whether you talk with respect to engineering sciences, whether you talk with respect to physical sciences, biological sciences, social sciences, that is the reason why humanities and social sciences should be understood by all of us. The knowledge that is segregated, that is divided with respect to areas, specializations, all of them needs to be understood in its context. And what provides the context? It is the social reality. How do you correlate knowledge in a given domain with the cultural reality, with the social reality, with the socio-political compulsions? Okay, how do you understand the law of nature, okay, in its totality? And for doing that, you require the understanding of humanities and social sciences. Say for instance, if you are trying to understand the effect of a particular bacteria, a virus, any microbe, how it affects behavior, how it affects the organism, human being, you start looking at it from a pure biological point of view. If you are trying to look at a particular type of a wavelength, say for example, you are emphasizing on the understanding of the effect of radiation on human life, you are looking at things from a physical point of view. You are looking at the corresponding changes inside the body, you are looking at the physiological side of the understanding of the information. You are trying to understand why, despite knowing the risk that is inbuilt in the process, why still human beings engage into it. You are looking at it from a pure behavioral point of view. Why society at large admire things which has full of risk. You are trying to understand things from a pure sociological point of view. Why people use particular set of words to explain those experiences. You are trying to understand things from the linguistic point of view. So, there are a whole lot of things, and then finally you try to combine all of them to say that what are the guiding principles in life. Then you say you are looking at life, you are looking at humanity from a pure philosophical point of view. And this is what social sciences courses provide you. They provide the context to you in which you would be finally positioning the understanding of the knowledge in any given domain. It could be engineering, it could be sciences, it could be medical sciences, it could be social sciences stuff, it could be humanities stuff. So, contextualizing the knowledge is what humanities social science courses help you obtain.